Welcome back to the Calculus Analytic Geometry. So, I hope that you are doing well and working on your assigned exercises, and you have been watching the lectures very carefully. So what we did in our last discussion, we basically talked about optimization techniques, that how, if you have been given say a function of single variable, then how to optimize this function. Okay? How to optimize this function. By optimization, I mean how to maximize, okay, and minimize the functions, actually, such kind of functions. So far we have kind of covered three basic methods for computing and knowing the maximum and minimum and point of inflections for a given function. So we have did what you call the closed interval method, finding the absolute maximums and absolute minimums, okay, which simply says that if you have an interval, a function is defined on an interval, okay, and then the absolute maximum and minimum will occur at either at endpoints or at a point C that lies in the interval A2. Okay, so that's essentially, it says that you're going to find your absolute maximum or minimum at what do you call these three possible points. We also talked about the first derivative test, okay, which essentially says that just have a look at the sign of what do you call look at the sign of the first order derivative, actually. So if this sign is, say, positive, okay, so if you have, for example, a critical point, say x equal to c, and before this critical point function is increasing, and after this critical point, say function is decreasing, then you're going to say that this x equal to c is a maximum, actually. Okay, it's a max. So it's like before c function is increasing, and after c if the function is decreasing, then x equal to c is a maximum. And we also talked about that if before c, in other words, before c function is decreasing, okay, and after c function has started increasing, okay, then this point x equal to c is going to be minimal. So this is just a snapshot of what do you call the first derivative test. And similarly, we talked about the second derivative test, which is much more what do you call easier, actually, okay, which simply says that if you have a critical point, say x equal to c, so it's a point where the derivative of the function is 0, and you compute the second order derivative of the function, and it turns out to be a negative number, then x equal to c is a max, okay, and if the second order derivative turned out to be positive, then x equal to c is a minimum. Then we talked about the reasons that why first order, second order derivative test, and closed interval test make sense, actually. So what we are going to do in today's discussion, we're going to hit mainly two topics. We're going to talk about some of the applications of optimization, actually, okay. Applications of optimization techniques that you have learned. Okay, we're going to use first order, second order, and closed interval test to find the maximum and minimum of a function in a practical situation. So we're going to do lots of examples with it, and then we will end our discussion today on talking about the anti-derivatives actually. Okay? Anti-derivatives, okay, which essentially, means that, usually what we do that, okay, if we know the function, then we compute the derivative actually. That, okay, so if you have been given a function, then you know how to compute the derivative. Now we will like to think backward actually. Okay, so if we have been given a derivative of the function, we will like to guess that what is the function whose derivative is this number actually. So it's like doing the anti of the derivative actually. Okay, so these are the two basic things that probably we're going to cover in our today's discussion. As previously, I talked about what do you call some of the methods, for example, some of the steps that we always take to solve the problems, practical problems. So the same steps would work here as well actually. So for example, let me say give some steps. Okay, you can do things at the way you like actually, but keeping in view these steps will kind of give you an additional support actually. That okay, if you are tackling a practical problem, then how to begin with it and how to, for example, solve it further actually. And another important thing is that it is not enough to just solve the problem actually. Okay, you have to kind of present the problem in such a way that your reader makes sense of it actually. Okay, so your reader should not use his intellect and understanding to make sense of your problems. You should when you are solving a problem, so it's like giving a running commentary actually. So you might have heard commentary over cricket actually. So when you are solving a problem, okay, practical problem, any mathematics problem, just writing equations and is not enough. You have to talk about the equations as well, that what they mean, how they come up, what steps you are taking, what methods you are taking. So it's like give the running commentary. Anyways, so here are some of the steps to, for example, solve, say, these problems are the problems of optimization types. Obviously, the first step is to thoroughly understand the problem actually, okay, without missing anything. So in other words, carefully reading the statements, okay, that making sense of it actually. Are there some words which you don't understand actually? I mean, if you are not understanding, for example, the language of a problem, solving it is going to come afterwards. If you're not understanding the language, you're not going to be able to solve the problem actually. So the first step is to make sure that you understand every single bit of the problem actually. Okay, and by understanding, you can also say that, okay, that what is known to you, what is, okay, unknown, and what you have been, so what quantities are given to you and what quantities you have been asked to find out actually. Okay, so that's all kind of included in step 1. Step 2, as I always say that, draw a diagram actually. Okay, drawing a diagram, if you have correctly understood a problem, drawing a diagram, okay, drawing a little sketch of, the kind of problem you are solving is going to hugely add a value into your solution actually. Otherwise, if you are solving a practical problem without drawing diagram, it's like solving a very abstract problems actually. Okay, and it will be kind of difficult for both your reader and sometimes yourself actually to what do you call, solve an abstract problem actually. So drawing picture is always a very useful thing actually. Step 3 always is to introduce the notation. Okay, so the notation is important. So all quantities, okay, that are known to you, unknown to you, denote them actually. So x, y, z, whatever. Okay, and also identify, for example, the function that you have to kind of minimize actually. Function, formula, okay, formula that you are interested in minimize actually, and how these quantities, okay, known and unknown, are related with each other through some function and formula. So the step 3 is pretty much what do you call important, for example, important step actually. So if for example, if you are talking about say area, okay, so you know that the area depends on length and width actually. So if you are, so for example, if you have area denoted by A, so if you are talking about that, okay, area is length and width, talk about it. So if you are talking about say volumes, so use appropriate notations, and height is h and so on and so forth actually. So whatever quantity is given to you, whatever quantities are given to you, or even those quantities which you don't know or which are unknown or which you are being asked to, for example, find out, give them names, and this is important things, and try to formulate a function and a formula. And then the fifth step is really to do the optimization actually. In other words, that to find the maxima and minima of the, what do you call, given function. So if you know the function, you know the quantities, you know the formulas, how these quantities are related, the last step is really to do the optimization actually, okay? And to do the optimization problem, you may use any one of what you call methods to find the maximum and minimum actually. So you also have to take carefully, think of that. Okay, do you have to find a local maximum, or you are being set to find, for example, a global or absolute maximum and minimum? Okay, then apply, for example, the method appropriately. So, for example, closed interval method is a method to find the absolute maximums and minimum actually. You can also find absolute maximums and minimums from what you call first and second derivative test, but for example, the first derivative test is very useful if you want to find the local maximums and minimum. So these are the steps. So make sense of the problem, draw diagram, introduce notation really, and notation, identify the quantities known, unknown, and see that how they are related, and then choose some of the method to do the optimization actually. Okay, so I hope that you got this sense, some sense of what do you call the results. So let's move on and solve some of the problems actually. Solve some of the problems. So the first problem is a very simple and an interesting problem, and the problem is that imagine there is a river is going on right from the middle of, say for example, village or some place actually, and a farmer wants to do the fencing around what you call a part of the river actually. So you have say a river, okay, the river, the water is flowing in it, and there is a farmer who is interested in do a kind of a fencing actually. So he wants to kind of make a wall around a specific area of around the river actually. And he want to say make the wall in such a way that there should be wall only on the 3 sides of the river actually. Okay, so he want to keep this end, the side of the river, open. Okay, so we just want to create the wall in such a way actually. Now what he has actually, so what is, for example, let's do the step 1. So the step 1 is really is making sense of the problem. So I kind of drawn the diagram. Okay, river, want to do the fencing, so you want to create, so for example, river is flowing like that, so you want to create a kind of a wall. Okay, beside along with the river actually. Okay, and he has some available fencing actually, so he has some amount of available fencing. Now what you want to do that, okay, given some quantity of the fencing, okay, what is the maximum area that this fencing can cover actually? Okay, so it's like okay, if I give you some piece of rope or some piece of, for example, thread, and I say you make a rectangle out of it, but try to make a rectangle, okay, that has a maximum area. So obviously you can make a lot of rectangle through a given thread, okay, but the question is that, okay, make such a rectangle which has a maximum area. So precisely that this farmer want to do, that he want to create a wall, okay, and he has some quantity of fencing available through fencing, and he has some quantity of fencing available, so, and he needs to figure out, or he needs some help to figure out that, okay, with this available fencing, what is the maximum area that he can kind of cover actually, okay, through this fencing. So how much of the fencing is available? So identifying the, understanding the problem. So fencing that is available, okay, fencing that is available is really 2,400 feet, okay, and he don't want to fence off here, he just want to fence off like this, okay, so you just want to keep this open. So the fencing that you want to do is around this part actually. So he just want to create the wall in such a manner. Wall, okay? Now, obviously, he has different possibilities. Maybe, so he's kind of confused that shall I make an area like this, or shall I make an area like this? So how should I, what kind of fencing should I create with this available, what do you call, fencing, so that a maximum area can be covered? Okay. So let's help him to solve this problem. So first of all, so this is the quantity that is given to me, and unknown quantity is the maximum area. Okay, maximum area, and you can know this maximum area if you can know the dimensions actually, that how, what should be the length of it and what should be the width of it actually, okay, what should be length of it and what should be the width of it actually. So this is unknown. So we did almost like the step 1. Drawn diagram, step 2 is also done. Now what are the quantities that are involved in this? The first quantity is that, okay, the total length of the fencing that is available is 22,400 feet. So we are talking about, say, area, and if you are talking about area, you should talk about, for example, length and width actually. So So this x is the length of the wall. So if this is x, this must be x as well. And you know, say call this width as, what do you call, y actually. So what should be the area that, what do you call, this width and length can cover? So obviously the area that this width and length can cover is a times xy. Obviously I must write that x is my, say, length, okay, and y is width. Okay. Now, since you want to create the three walls, you don't want to do the fencing, okay, so he has to create kind of a two such walls and then one such wall actually, okay, through the fencing. So and the available, what do you call, fencing is this actually. So in other words, if we combine, for example, these two walls, which are kind of representing the width or the length of the area, so 2x plus y is the width, okay, should be equal to what? So the farmer want to consume this this available fencing in creating the two such walls and one such wall actually. So this sum, the length of, say, this wall and this wall plus this wall should be equal to what? Should be equal to the available fencing actually. Available fencing. Okay, so this is what, these are the two basic equations that are kind of given to us actually. Now we want to maximize the area. We have learned the techniques. So the techniques that we have learned are, you know, you can apply the techniques, of the optimization, where you have a one dependent quantity and two independent quantities actually. Now the trouble here is that the quantity that we want to optimize, say area, depends on two quantities, which is x and y. So if the area can depend, for example, on one quantity only, then I can apply my optimization technique to find out the maximum area that I can cover actually. And it is not difficult. For example, if you call this equation number 2 and call this equation number 1. So if I, for example, isolate or eliminate or get the value of y from here and substitute it here. So from 2, I can say that I can get this value, which is 2400 minus 2x. Obviously, the units of these lengths are feet actually. Okay, both are in feet. Okay? Both are in feet. So it's going to be y equal to 2400 minus 2x actually. So the area now can be and say use in 1. Okay. So the area now is going to be what? Is going to be x times y minus 2400 minus what do you call 2x actually. Okay. So this is what it is going to be, and you can simplify it even further, and now you can say that your area is a function of x, so it's 2400x minus 2x squared actually. So this is what the area is. So why I made this substitution, I must say this again, that since the quantity that is unknown to me that I want to optimize depends on two variables, and the techniques that you have learned for optimization, in those techniques you can have at most one independent quantity. So this means that you have to kind of get rid of one quantity out of it actually. So using this, I kind of got rid of one quantity, say y, out of my formula, and I got this actually. And I want to optimize this function. So the first step always to optimize the function is to find, to compute the critical points actually. Okay? The critical points. In other words, the point where the area changes its behavior actually, and how you can find it, you can differentiate it and say equate it to 0, and that would give you, and solve this equation, and that would give you the required result actually. So if you do this, what you're going to get? You're going to get, so if I differentiate it, so you're going to have 2400, x will become 1 minus 4x equal to 0. Okay? And this means that 4x is 2400 and x is really, what do you call, 600 actually. Okay? This is what is really the value of the x. So this is a critical point. And now I need to say that whether this critical point, I don't know, as I said, this is just a critical point. This critical point, we know, can be maximum, can be minimum, can be anything actually. So we can, for example, we try to find the critical point actually. Try to find that, okay, whether this critical point is a maximum or minimum actually. The easiest one could be, my hot favorite one is really, what do you call, if you apply the second derivative test actually. Okay, so give a try first to second derivative test actually, because it gives you a very quick way of finding you don't have to do a lot of checking actually. Okay, you just have to find out the what do you call, the sign of the second order derivative at the critical point, and that would give you the result. So let's calculate, say, second order derivative. So what would be the second order derivative? So the first order derivative is 2400 minus 4x. So the second order derivative at x is going to be minus 4 times 1, so it's going to be minus 4 actually. Now this is something interesting. So this shows that no matter what x you put, a double prime is negative. So if I say, for example, substitute this 600 in this formula, it is, this is not going to change anything, and this would be still negative actually. So this has a negative sign. So if it is a negative sign, then the second order derivative test, okay, tell you that x equal to 600 is a maximum point actually. Okay, it's a point where the area is going to take its maximum value. So we know the width of what do you call, the width of the length of this area. Okay, now what would be the width? So we know that how the width and the length are related. So just take this and say substitute it into y. So what are you going to get? So 2400 minus 2 times of, say, 600. So it is going to be 1200. So 2400 minus 1200 is going to give you the 1200 actually. So this must be the dimension actually. So so through this available fencing, you can make a rectangular region whose dimension are 600 and 600. So in other words, use the 600 feet fencing, what do you call, feet fencing here, 600 feet fencing here, and fencing here, and 1200 feet fencing here, and the maximum area that you're going to get out of it, okay, the max area that you can get out of this available fencing